Hello everyone. In this video, we will explore advanced polarimetric radar indices derived from Sentinel-1 SAR data using Google Earth Engine. Unlike optical remote sensing, synthetic aperture radar data operates under all weather conditions and during both day and night. This makes it highly effective for continuous monitoring of vegetation and land surface properties. Here, the highlighted yellow region represents our study area, and all analysis is conducted within this boundary using Sentinel-1 data collected between June and September 2025. In this workflow, we use dual-polarization SAR data, specifically VV and VH bands. A median composite is generated to reduce speckle noise and to obtain stable backscatter values. Now, let us examine the outputs one by one. Output 1. Area of interest. This yellow shaded region defines the study area where all computations are performed. Output 2. Entropy. This layer is displayed using a color gradient from blue to yellow to red. Blue areas indicate low entropy, meaning simple or smooth surfaces such as water or flat land. Yellow to red areas indicate higher entropy, representing complex scattering, typically associated with vegetation or heterogeneous surfaces. Output 3. Biomass proxy. This layer appears mostly in shades of green. Darker green regions indicate higher biomass, meaning denser vegetation. Lighter green or yellowish areas represent lower biomass or sparse vegetation. Output 4. Index-based classification. This layer uses distinct colors for land cover classes. Dark green represents dense vegetation. Light green indicates sparse vegetation. Gray represents bare land or urban areas. Blue corresponds to water bodies. Output 5. Biophysical RGB composite. This is a multicolor composite image. Green shades dominate in areas with vegetation, water content. Red tones indicate biomass presence. Blue components represent soil moisture. The combination of these colors helps visualize multiple physical properties simultaneously. Output 6. Polarimetric RGB composite. This layer appears in mixed colors such as purple, pink, and blue. These colors represent combinations of entropy, alpha, angle, and span. Different color variations indicate different scattering mechanisms such as surface scattering, volume scattering, or double bound scattering. Output 7. Vegetation indices RGB composite. This layer appears mostly in reddish tones with some variation. The red dominance indicates strong vegetation signals, while slight variations in color represent differences in vegetation density and condition. Output 8. Radar Forest Degradation Index or RFDI. This layer is primarily green. Darker green indicates lower RFDI values, meaning dense and healthy vegetation. Slightly lighter green or small red spots indicate degraded vegetation or non-vegetated areas. Output 9. Dual-polarization Radar Vegetation Index or DpRVI. This layer appears in light green shades. Higher values, shown as brighter green, indicate vegetation presence. Low values appear as pale or faded green, representing less vegetation. Output 10. Radar Vegetation Index or RVI. This layer appears mostly dark green. High values indicate dense vegetation, while small red or lighter patches indicate non-vegetated or built-up areas. In conclusion, polarimetric radar indices provide a robust alternative to optical remote sensing techniques. They enable continuous monitoring regardless of weather conditions and offer physically meaningful insights into vegetation structure, biomass, and moisture. This approach is highly suitable for applications in agriculture, forestry, and environmental monitoring.